So hi, we're interested in automating RLHF for robotics with pre-trained vision models, and I'm Daniel. This is Oliver and Song Ho. This work was done as part of the AI Hackathon at the 2023 Cumberland Lodge Retreat for the UCL FAI CDT. So our motivation is that task design in reinforcement learning is very difficult. For example, consider this video of an agent doing a backflip. It will be very difficult to design a reward function for this, mainly because the reward is non-trivial, and also it depends on full trajectories, not just individual states. RLHF is a robust and flexible method for task design that solves this problem by using a human preferences to implicitly specify a reward function. Using this approach, OpenAI was able to train a Hopper agent to perform a backflip in a simulated environment with less than 900 bits of feedback. However, human feedback itself is expensive and limits the scalability of RLHF. We are interested in whether we can automate most or all of it using, for example, vision models. In this case, it's plausible that we could get a vision model to provide a sufficient visual feedback for the agent to perform a complex task in simulation. So therefore, we propose RLVF, RL from video feedback. How it works is that we will assume access to a video language model which can compute embeddings of both text and videos. Given some text description of a task and a video of the task execution, we compute the embeddings of both, and the similarity of the two embeddings can be used as a reward function. Intuitively, a higher similarity means a higher reward because it means that the agent's video is closer in semantics to the text description of the task. The problem is that we don't have such a video language model yet, at least not one that applies generally to robot environments. Therefore, we want a simple proof of concept to validate this idea, and so we choose to train our own preference model. In the following work, we do not consider text, but consider video models fine-tuned on a single fixed task. Our overall workflow is to obtain expert as well as noisy trajectories from policies of varying competence to train a preference model, which can be used interchangeably with a human oracle. The preferences can be used to train a reward model, and the reward model can then be used to train a final agent through standard RL techniques.
So for trajectory creation, for simplicity, we chose the environment Carpool V1, and we used DKN algorithm to produce trajectories with differing performance levels, ranging from very initial level, like from 0 to 100 reward, and then up to like higher than 490. And in trajectory, it included all the items which are necessary for reinforcement learning, observation from numerical information, image, action reward, and episode termination.
So my task was to replace the human feedback in RLHF with the automated feedback. So I trained a model to take in two different types of trajectories from a well-trained policy and a poorly trained policy, and for it to output its preference as to which was better. On the right, you can see the videos of two different policy behaviors and their predicted scores. The score being higher for the policy which is able to balance the carpole. We initially chose an LSTM model to train this preference to predict these preferences, but it found that it struggled with long-term dependencies of long trajectories, so we then opted for a transformer architecture which functioned well. So we can prove that you can accurately train a preference through trajectories.
Yeah, great. And finally, assuming that we have access to preferences from a learned model or any oracle, we can learn a reward model through standard RLHF techniques. So for this section, we obtained a diverse data set of half cheetah V2, the D4RL data sets of the random, medium, and expert policies, and combined them into a combined data set. We sample pairs of episodes as well as compute the analytic preference but just by comparing the reward of each episode. For example, if X0 had higher return, then that one would be preferred. Using these analytic preferences, we trained a reward model to minimize the loss given here, which is standard in RLHF. Our reward model was also a transformer. We tested 2 different architectures, transformer and MLP encoder for the reward model, and found that the transformer does much better. Our predicted episode returns correlate quite well with the dataset of origin, with the scores for the expert being higher than the medium and the medium being higher than the random, with good separation of scores. Finally, assuming we have a learned reward model, we can use it to train our agent using RL. Because our reward model predicts trajectory level returns, we instead compute the stepwise reward from the consecutive difference of episodic returns. And this allows us to plug our wrapped environment into a standard reinforcement learning algorithm. We trained the agent with the learned reward model and measured both the training history of both the learned return as well as the oracle return. So we found that while the agent learned to maximize the learned return, the oracle return remained low, which means that the learned reward model was not powerful enough, and possibly the agent was exploiting some inaccuracies in the reward model to achieve such a high performance. Future work can try to address this by training a better reward model. So our contributions are that we have investigated a simple framework to use a pre-existing preference model to learn a reward model, and we hope that this framework is compatible with pre-trained video language models in the future. We validated this framework with our own preference model and investigated using the learn reward model to train the agent. We noted the problems with reward model over-optimization, which has also been noted in other RLHF works. One related work is Mind Dojo, where the authors trained a video language model on a large data set of Minecraft YouTube videos, and were able to train an agent that is capable of accomplishing many diverse tasks in a complex environment of Minecraft. However, this video language model is specific to the Minecraft environment and does not transfer to robotic environments. For future work, we are interested in the active learning setting where both the reward model and the policy can learn from human feedback. In theory, most of the examples generated by the policy can be automatically labeled by the reward model, whereas in some edge cases, a human annotation may be needed to specify the true preference. This can be used to update the preference model on regions where it's uncertain. Other future works include improving the limitations of this study by improving our preference models, reward models, and training on more environments. Thank you.